Welcome back, students. So now today we are going to take some practice problems on sterilization and heat transfer operations in reactors. Let's see the problem given on the slide, where we need to estimate the batch sterilization time for beta stereothermophilus organism, and the Arrhenius constant is given. The activation energy is also given, and the universal gas constant value is also known. The sterilization is said to be successful if we can have one only remaining in 10 to the power of 7 spores after the process of sterilization done at 121 degrees centigrade. They have also asked us to calculate what temperature should be maintained to achieve the same level of sterility when the sterilization time is given as 30 minutes. Okay, so let's first solve the first part of the problem, which was to estimate the batch sterilization time. Now, first we'll consolidate all the information which is given to us about the process. So, here is the list of information which is given to us. So, Arrhenius constant is given, activation energy is known, R is also given, and temperature for sterilization is also given, which is 121 degrees centigrade. So, to keep the consistency of units, we will convert it into Kelvin. Now, what else is given? The number of viable cells we can assume to be 10 to the power of 7 spores in the beginning. So, for successful sterilization to happen, only one should be remaining. So, we can assume the N0 value, which is given here as N1, is 10 to the power of 7, while the final number of organisms after sterilization cycle is 1. So, this is N value. Now, we know that as per Arrhenius equation, your thermal death rate constant is a function of temperature given as the Arrhenius model or equation, and we know this is what is Arrhenius equation. Now, here Kd, which is thermal death rate constant, A is your Arrhenius constant, E is the activation energy, and T is the temperature for sterilization. Now, we also know, assuming that the thermal death kinetics follows a first order kinetics, then ln N0 by N will be equal to Kd T, where T is your sterilization time. So, minus sign has gone, therefore, the N0 came up. So, now we have to find the batch sterilization time. For that, we must calculate the value of Kd first, because we need Kd here. So, Kd can be calculated using Arrhenius equation, where T is known, the constant values are given. So, then if you substitute all the values, you can find the value of Kd, which is given here as 4.5 minute inverse, because rest of the values are given to us in the Arrhenius equation. And using that value of Kd in the first order degradation kinetics, we can find the value of time required to reach the desired sterility, where N0 is your N1 as shown here and N is your N2, which is shown here. So, if you substitute all the values here, do the rearrangement to get the value of T, then T is being represented as THD, which is holding time for batch sterilization, and you get the time for sterilization. We are assuming, if it is holding time, we assume no killing during heating and cooling. It is being sterilized at 121. Now, in the second part of the problem, if the same level of sterility is to be achieved in 30 minutes, then what should be the temperature at which the sterilization can be done? So, if this time for sterilization can be changed to here in this equation, if this can be changed to from 3.5 to 30 minutes. So, now using the first order degradation kinetics, the value of the thermal death rate constant will be calculated giving the same sterility to be maintained. So, N1 and N2 remains the same. N1 is the initial number and N2 is your final number. So, here ln N1 by N2 is equals to K dt. This has come from dN by dt being a first order kinetic equation is proportional to N. So, your dN by N was K dt. So, this was from the batch sterilization time and this is from some N1 to N2. This is first order degradation kinetics. So, minus, so this becomes ln N1 by N2 which is equal to K THD. This is what is given here. So, then N1 and N2, the sterility level is the same. So, this becomes, you can obtain the N1 and N2 values from the problem given here and you can substitute in this equation to get the value of Kd. Now, once we have got the value of Kd, by the Arrhenius equation we can obtain the temperature because E and R will remain the same. A is given, so we can find the using Arrhenius equation. What was Arrhenius equation? Kd is equals to A e to the power of minus E by RT. So, this is how we can calculate the temperature. Let us see the second problem. The temperature history of heating and cooling of a 40,000 liter tank during sterilization of the medium is, so we have been given a profile of how the temperature is changing. So, from 0 to 15 minutes the temperature is at 85, from 15 to 40 minutes the temperature is at 121, from 40 to 50 minutes again it drops to 85 and from 50 to 60 minutes it is at 55 and this is how it cools down. Greater than 60 minutes the temperature then is 30. This medium contains vitamins which are heat labile. They have an activation energy of 10 kilocalorie per gram mole. The Arrhenius equation constant is given. Assume the destruction by heat is following the first order and the initial concentration of vitamins in the medium is 50 mg per liter. The R universal gas constant value is given and the initial number of spores present in the medium for sterilization is also given per liter. Now, spores have the E value of 65 kilocalorie per gram mole and the thermal death rate constant at 121 is 1.02 per minute. Okay. We need to first find the probability of successful sterilization. First, let us list down what is given in the problem. So, here is the list of information which is given in the problem. The volume is given as 40,000 liters. For vitamins, the E value is given and the A value is given. For the Arrhenius equation, the initial concentration is known, R value is given, the initial number of spores per liter, the concentration of spores in the medium is given, and for the spores the E and the Kd value is also given. Now if you see the profile of temperature at 121, which is the holding temperature generally for sterilizations, the time is between 15 to 40 minutes, so which is 25 minutes. So for 25 minutes the temperature is being maintained at 121 degrees C, which is generally the sterilization temperature. So we will take that, the holding time. Now vitamin destruction is of the first order. So dN by dt is equals to minus Kn. So the probability of unsuccessful sterilization would be 1 minus P naught T, where P naught T is the probability of successful sterilization. And what is probability of successful sterilization? That none of the organisms remain. So if Pt is the probability of survival for each of the organisms, then for them not to survive, the probability will be 1 minus small pt, and none of these organisms should not survive. So the probability would be 1 minus pt to the power of n naught. So the probability of successful sterilization would be 1 minus pt to the power of n naught, and the probability of unsuccessful sterilization therefore will be 1 minus the probability of successful sterilization. So the probability of survival is e to the power of minus kd t. So this has been substituted here, and this is obtained from the first order degradation kinetics, the death rate kinetics of the organism. So if we substitute here, we will get this equation for probability of unsuccessful sterilization. Now this can be expanded using Taylor series expansion. So when you expand equation 1, you get equation 2, and then taking the first term constant out common, it can then be an infinite exponential series where the sum can be given as, for this infinite series can be given as shown here in equation 3. So you can check back on the Taylor series for expansion as shown in equation 2. So then if you substitute now Kd value, the time for sterilization, the initial number of spores present, all that is known in the problem. So if we substitute that, we will see that probability of unsuccessful sterilization comes out to be, so if the probability of unsuccessful sterilization is this, then the probability of successful sterilization would be 1 minus this value, which will be 0.99. So let us see the second part. The second part is what fraction of vitamins which are heat labile components during this process of sterilization will remain active. So how do we find that? The initial concentration is given, the final concentration is to be obtained, the time for which they are exposed to sterilization temperature is given. So we can determine the value of the degradation constant. To obtain the value of degradation constant, we will use Arrhenius equation, where the deactivation energy and the Arrhenius constant value is given, and it was calculated as 0.029 minute inverse. Then the same Kd value has been substituted in the first order degradation kinetics, and we get the final concentration of the vitamins during the sterilization operation after degradation. So the fraction of active vitamins would be the final concentration to the initial concentration, which comes out to be 0.48. Let us see another problem. a 15 meter cube chemostat is operated with dilution rate of 0.1 hour inverse, a continuous sterilizer with steam injection and flash cooling delivers sterilized medium to the fermenter. Okay, so this is a continuous heat sterilization process. Medium in the holding section of the sterilizer is maintained at 130 degrees C. So the holding temperature we know is 130 degrees C. The concentration of the contaminants in the raw medium is known, which is 10 to the power of 5 organisms per ml. This is the load. An acceptable contamination risk is 1 organism every 3 months. We cannot go beyond that. So, after every 3 months, there is only 1 organism. The Arrhenius constant and the activation energy for thermal death is given. A value is given and the activation energy is given. The inner diameter of the sterilizer, the pipe diameter is given as 12 centimeters. Now, at the sterilization temperature, which is 130 degrees C here, the fluid properties including the density and the viscosity is known. Now, it is set to assume that the fluid is under perfect flow conditions, and we need to determine the length of the holding section. Now, again listing down the information which is given in the problem. So, the volume given to us is 15 meter cube of the raw medium. In this chemostat continuous sterilizer, the dilution rate is 0.1 hour inverse. So, the volumetric flow rate can be calculated using the dilution rate and the volume. We know how they are related, which comes out to be 1.5 meter cube hour inverse. So, dilution rate is nothing but F by V, where F is the volumetric flow rate and V is the volume. Then the temperature is given as 130 degrees C, so we convert it into kelvins. The initial load is 10 to the power of 5 number per ml. So, we must find out how much will be the total number as per the volume. The pipe radius is 6 centimeter. The area would then be, it's a pipe, so the cross sectional area is pi r square, and the R, A and E value are given. Now, from the information which is listed, we can calculate the linear velocity, the fluid velocity in the pipe, which can be given as the volumetric flow rate divided by the area of cross section. So, it comes out to be 132 meter per hours. Now, the Arrhenius constant is given, the activation energy at temperature 130 degrees C is also given. So, we can find out the thermal death rate constant. So, two things can be obtained, one is the linear velocity, the other is the thermal death rate constant. Now, because 1 in 3 months is acceptable, one organism surviving. So, in 3 months, which means what would be the total amount of organisms? So, we need to calculate the number of cells entering the sterilizer. So, per ml of the raw medium is 10 to the power of 5 ml. So, we need to see how much medium would have been processed in 3 months. 1.5 meter cube per hour. So, this will be 1.5 into 90 into 24, this much meter cube processed into 10 to the power of 5, 6 ml. So this will be the total amount of cells. So if we know that the acceptable limit, let's assume only one organism remains, N0 is not known, we need to calculate is equals to the thermal death rate constant into the holding time. Now KD value we have obtained from here. Time for holding needs to be calculated if we know the other unknown is the initial number of cells. So the initial number of cells can be calculated by finding the total amount of raw material, the volume of raw material which will be processed in 90 days, because 1 in 3 months is acceptable. So we will find if the final is one organism, the initial would be whatever number of organisms have entered in these 90 days. So we can calculate the volumetric flow rate is given, total time is given, and 10 to the power of 5 per ml. So therefore we will multiply it to get the total number of initial amount of cells in the medium. So at the end of the sterilization, we can find what will be the time of sterilization required by the first order degradation kinetics. Now if the time of sterilization is known, we know in the holding section of the continuous sterilizer, this time is given is related to the length of the holding section by the linear velocity. So linear velocity we calculated previously, which if multiplied by the time it spends in the holding section, we will get the total length of the holding section. So this will be 14.2 meters.